Let's look at this idea of polynomial division. Sort of going back to long division. Yeah, you remember that from primary school days, where you used to do the long division? It's the same division formula that you would have seen back in primary days, except we're dealing with polynomials rather than numbers. Right? So AX is the divisor, QX is the quotient, RX is the remainder, PX is obviously the polynomial. The degree of the remainder is always smaller than the degree of the divisor. Because if the degree is bigger, it means I can keep going, I can keep dividing. Okay. And QX and RX, so the quotient and the remainder are unique, which just means they're different. Because if they were the same, you could factorise. So you wouldn't have completed the factorisation yet. I just picked one out from an HSC, 1998. Okay, they find the quotient, the remainder. They want us to do x to the 4 minus x squared plus 1 divided by x squared plus 1. So let's set it up. Just like we did with numbers back in primary school, whatever we're dividing by, we put over here, x squared plus 1, what we're dividing into. What's really important with polynomials though, is leave a space, or I write it just by putting 0 as the coefficient, for every single possible power. So you'll notice what they're asking me to divide into doesn't have an x cubed term. But when I'm doing my division, I might create an x cubed term. So just in case, I put 0 ones in there. So I've got nice columns, one for the powers of 4, one for the powers of 3, and so on. And when you're dividing, all you're really doing is looking at the leading terms. So we're looking at, oh, well, what's x4 divided by x squared? Ooh, geez, that's a bit hard. x4 divided by x squared. That'd be x squared, of course. Then we multiply out. So we go x squared times x squared is x to the power of 4. X squared times 1 is x squared. I don't have an x cubed term. And we subtract. Minus 2x squared. But we also bring the other terms down. So now, there's my remainder, but hang on a sec. The remainder is the same degree as the divisor. We can keep going. Let's do it again. X squared into minus 2x squared is, of course, minus 2. Multiply out. Excellent. Minus 2 minus minus 2, that disappears. 0 minus 0, that disappears. 1 minus minus 2 is 3. Now my remainder is a constant. Dividing by x squared, that's where I stop. So what have they done? They've simply said, find the quotient and the remainder. So there it is. Quotient is x squared minus 2. My remainder was 3. Let's do another one. Ooh, 1988, the bicentennial year. It was a good year. Oh, you would have enjoyed it. Trust me. It's a really good year. Okay, let's set it up. Okay, same thing. X squared into 2x to the power of 4, 2x squared. Multiply out. 2x to the 4 minus 6x cubed plus 2x squared. Do a subtraction. This, I guess, is where most of the mistakes happen with the negatives. So be careful. Minus 10 minus minus 6 is minus 4. 12 minus 2 is 10. Bring the other terms down. Yes, I can keep going. X squared into minus 4x cubed minus 4x. Multiply out. 10 minus 12, negative 2. 2 minus minus 4, 6. Yes, I can keep going. So we go another time. Negative 2. Minus 6x minus 2. Subtract, subtract. Minus 3 minus minus 2. Minus 1. That's where I will stop. Now, what have they done? They've simply said divide it. Well, I suppose technically I've done that, haven't I? I don't like leaving my answer like that. Of course. Well, I didn't see part 2. In the test, I would have known part 2 was coming, so yes, I would have left it like that. It just feels like I should write the, quotient times that. But in fact, that's what part 2 is saying to do. So hence go and write it. So all right, there we go. It's x squared minus 3x plus 1, 2x squared minus 4x minus 2, and the remainder, minus 1. You get questions like that, you just say, thank you very much. I'll take those marks. Polynomial division is also a great way of finding features of graphs. So if you've got one of those graphs where you've got a function, a polynomial on top of another polynomial, you do your polynomial division and rewrite it as quotient plus remainder over divisor, and it tells you a lot of information. We know the bottom of the fraction can't equal 0, so we solve that. That gives us our vertical asymptotes. The quotient turns out to be the horizontal or oblique asymptote. And then the remainder is useful because you solve that, and if there are solutions, that is where it will cut the horizontal or oblique. And that's a mistake people often make. They think, oh, asymptote, can't touch. You can. You're allowed to cut asymptotes. You can't cut vertical ones because they're not in the domain. But you can cut horizontal and oblique, because all a horizontal and oblique asymptote is telling you is this is what the curve is doing as it's going out to infinity. So if it's not near infinity, it can cut it. And of course, any number is not near infinity, so it can cut it anywhere. So the top of that fraction will tell us where it cuts. So let's have a look at this one. So it's already been done for us. X plus 8x on x squared minus 9. So righto, vertical asymptote, I know it's going to be a plus or minus 3. So let's put those in. Whee! There we go. There's an oblique asymptote at y equals x. Let's draw that. There we go. Now, if we look at the top of the fraction, it is actually going to cut that oblique asymptote at x equals 0. So I'll just plot that point in there. I know that's where it's going to cut that asymptote. Well, the other things we know curves bend towards asymptotes. So let's, there we go, put it in. See, I'll start over here at the right-hand side. It's got to bend towards the asymptote. So it's either in the section that I've drawn here. The only other thing it could have done is to be underneath it, and it would curve to the asymptote, come down, and go down to negative infinity. But it can't do that, because we've decided there's no x-intercepts over here. So it would be impossible for it to come down and cut and go down there. So therefore I know it must be trapped in this little section here. I'll come back to the middle later, but over here on the left-hand side, same thing. Must be trapped in this little section here, because if it was in the other bit, it would bend towards this asymptote, it would come up and go up towards positive infinity. It would need an x-intercept, which we haven't got. So it must be trapped in here. Now this second one in the middle, actually would be the third one. Back to that 2 plus 1 problem, isn't it? Now, it's either going to do what I've got, or it might be the reflection of that. So really all I need to do is test a point to see whether it's positive or negative. So I could just sub in, well, 1's an easy number to sub in, and 1 would turn out to be negative. Negative 1 would turn out to be positive until we know, okay, well, that's what it's doing. So there's our graph. Oh, asterisk on the 14. I think I know what that question is. Okay.